Let's start the third installment of the lecture series of Fundamentals of Optical Coherence Tomography. And today I'm going to talk about the resolution and the sensitivity of OCT, right? And the first half, or technically maybe first 1/3 of today's lecture is dedicated for the resolutions, including the axial resolution and the lateral resolution. And most of the part of today is going to be dedicated for the sensitivity issues. And here, first, I'm going to talk about how we can think about the signal energy of the OCT. And then, the first, I will break down the signal-to-noise ratio into signal and the noise. And then the noise is going to be broken down into 3 components: the shot noise, and ring, relative intensity noise, ring, and also the detector noise, detection noise or detector noise. Okay, and then I'm going to talk about the sensitivity and and then I'm going to talk about the signal-to-noise ratio and define the sensitivity, and then see which kind of property of the OCT sensitivity has. Okay, so then let's start the first section of today's lecture. It is about resolution. Okay, and the resolution includes 2 points. The one is an axial resolution. Similarly, we also call it as a depth resolution. And the second resolution is lateral resolution. And the axial resolution is already the theory of axial resolution is quite well established. And here I'm showing the equation, the established equation of the estimation of axial resolution of OCT system with a Gaussian spectrum. Okay, and here again, the Gaussian spectrum is one of the keywords. So this means this theory based on an unproven fact of the OCT system is using the Gaussian spectrum. And that was quite true when, say, at the old days, like the 90s and on the early 2000s. But the current OCT system is using a little bit special type of superluminescent diode or sweep source. And this assumption of the Gaussian is not always true. But anyway, still this equation can give you a good estimation of axial resolution. And then let's see the equation itself. Here is delta Z, or technically capital delta of Z, is frequently used as a depth resolution, symbol of depth resolution. Okay, and here are 4 times natural log of 2 divided by n. Maybe this one, 4 log 2 is one of the constants. And by assuming the Gaussian spectrum and the Fourier transform it, you can get this constant. Okay, and delta K is the bandwidth of the light source in K, wave number K. And N is the refractive index of the sample. And in a textbook theory, this N is frequently missed, or simply assumed as N equals 1. Okay, but also, if you have some experience with the OCT, very frequently you saw in a paper that the axial resolution is, for example, 8 micron in tissue or 8 micron in air, right? If it is written in air, it assumes n equal 1. And if it is denoted as in tissue, frequently it is assumed as 1.38. Okay, it's a kind of magic number. In the old days, anybody was writing it as n is 1.38. In tissue, n equals 1.38. But in these papers, it is very frequently missing. Okay, but anyway, if it is written as in tissue, the refractive index is assumed as 1.38. Okay, and then, so then if you have some experience, you've already seen this equation, but not in this form. Okay, and the point is here. So essentially, the resolution, depth resolution of OCT is defined by the bandwidth of the light source in K domain. But most of the cases, the specification sheet, in the specification sheet of the light source, you found the bandwidth in nanometers. Okay, so it might be very convenient to convert this equation into the wavelength domain. So then just substitute this delta k by lambda equation. In reality, you can just compute the derivative of the equation of k and lambda and then substitute it. And it gives you this equation. It's a quite well-known equation. The first, the constant becomes this guy, 2 log 2 divided by pi. It's around 0 0.4, sorry, 1.44. I mean, just forget. Yeah, 0.44. Okay. And then n still here, and the center wavelength squared divided by the bandwidth in wavelength. Okay. And then this can be simplified as something like a 0.44 divided by n times squared center wavelength of the light source divided by the bandwidth in wavelength. And this equation gives you 2 important points. Maybe 2 important points and 1 moderate point. The 1 point is resolution, practical resolution of the OCT is inversely proportional to the refractive index of the sample. Okay, so the axial resolution normally becomes higher in a tissue than the air. Okay, in a factor of 1.38. And if it's in the water, it's 1.34. Okay, and then the second point is this guy. Maybe this guy is the most well-known point. The bandwidth, the depth resolution of OCT is inversely proportional to the bandwidth of the light source. So more the bandwidth gives you a higher the depth resolution. Okay? This is a quite well-known fact. But another fact frequently people miss is this term, this numerator. So the resolution of the OCT is proportional or worsen as increasing the center wavelength of the light source, even in a power of 2. So this means shorter wavelength gives you better resolution, even in a power of 2. It means the shorter wavelength OCT, like 840, easily gives you, more easily gives you the higher depth resolution than that of 1.3 step source. That's the reason why for the high resolution imaging, we frequently use the short wavelength. And by some reasons for the short wavelength, we most of the cases we use the spectral domain OCT configuration. Okay, and recently some of you already know about a visible light OCT. Recently there are emerging development of visible light OCT, and it is specially utilized for the high resolution imaging. And the reason is actually the visible light even more easily gives us very high resolution than 840 near infrared, Okay, the visible light can more easily gives us the higher depth resolution than the near infrared light. Okay, so let me summarize. The trick to improve the depth resolution OCT are 2. The one is quite well known. Broaden the light source. And 2, sometimes it misses, but make the center wavelength short. Okay, these are 2 points of the axial resolution of the OCT. And so then let me give some examples of the depth resolution of OCT. For example, for 830 nanometer, most of the cases we are going to use a spectral domain OCT for this, right? And for 830 nanometer center wavelength and the bandwidth of 50 nanometers, in-air depth resolution becomes 6.1. Okay, here the refractive index is assumed to be 1. And if it's in tissue, it becomes 4.4. As I've already mentioned, it becomes slightly better than in air. And here the refractive index is assumed as 1.38. Okay, then let's think about a slightly longer wavelength. for example, 1.05 micron swept source OCT. And one of the typical bandwidth of the 1.05 swept source is around 70 nanometers. It becomes better and better, but as an example, let's assume 70 nanometers. Okay, and aware that the wavelength, the bandwidth of this guy is better than 830. Okay, here it's 50 and it's 70, and almost 50% or 40% better than 830. But the resolution in air is 7.0. It's worse than that of 830. Okay, so that the effect of the center wavelength. The center wavelength of 1.05 is slightly longer than 830. It results in this significant reduction of the axial resolution because the center wavelength affects the depth resolution in power of 2. Okay, and then this 0.5 becomes 5.0 in tissue by assuming the refractive index of 1.38. Okay. Then I just gave a brief summary of the depth resolution of the OCT, and then I also would like to give a very short introduction and a very brief idea of the transversal resolution of the OCT. Okay, but before talking about it, I would like to clarify that transversal resolution of OCT is still very controversial. And even OCT guys were not that much paying attention for the transversal resolution so far. And also, it pretty much depends on the system configuration. But there is one widely accepted, it's not estimate, but measure of the transversal resolution. It's the beam spot in a sample. Okay, for the scanning OCT, we make a beam spot in a sample by the objective lens. And the spot size is frequently used as a measure of the transversal resolution. And in reality, the transversal resolution is defined by the incident pupil and the detection pupil and the scattering property of the sample. Actually, the transversal resolution is not only the function of system, but also the scattering property of the sample. So it's quite hard to clearly define it. Maybe some of you already saw several papers discussing about it, even the recent papers, and also the confocal function, how we can define a confocal function. And these difficulties are stemmed from this issue. Okay, but anyway, one of the well-known and a well-accepted measure of the transversal resolution of OCT, the spot size in a sample, and this is defined by this equation. Okay, so delta x is widely used as a symbol of the transversal resolution of the OCT. And in this equation, what we can see is first, 4 over pi is a constant. Okay, and then lambda c, center wavelength. So this means the transversal resolution of OCT is in proportional to the center wavelength. Okay, and this means the center wavelength doubly affects the resolutions. The first to the axial resolution. It affects in the order of in the power of 2, right? I mean this equation. And then it also affects the transversal resolution in the power of 1 these days. And a shorter the wavelength gives you a better the transversal resolution. Actually, this is another reason why for the high resolution OCT system, people prefer to use the short wavelength. Okay, and then another factor here, F over D. F is the focal wavelength, the F is the focal length of the objective lens, or technically objective. Sorry, the objective lens, we are frequently using the word of objective, but technically speaking, the correct word is objective, only objective is known. Okay, the F is the focal length of the objective, and the D is a beam diameter at the pupil of the objective. So normally we illuminate the objective with the collimated light, and the D is the beam diameter of that collimated light. Okay, and if you define this beam diameter as a 1 over the E square width, the resolution is also defined as defined in 1 over E squared width. Okay, and if you define this D in FWHM, delta X again defined by FWHM. So sometimes I was actually frequently asked that in this equation, what is the definition of the transversal resolution? Is it FWHM or one over E squared width? But actually, this equation itself doesn't assume particular definition of the resolution. But its definition itself is tied between delta X and D. It's another point. And then I also would like to remind this part. F divided by D is something similar to the numerical aperture in a paraxia approximation, right? And the higher the numerical aperture, higher the resolution. It's a very standard way of thinking thinking in microscopy. And actually, OCT is also the same. Higher the effective numerical aperture result in higher the resolution. Okay, transversal resolution, higher the transversal resolution. Okay, and then let me show some example of the transversal resolution. Maybe you can give some idea of how the transversal resolution is in OCT. But assuming the focal wavelength of the objective at 30 millimeters, 3 centimeters, and a beam diameter of 2 millimeters, and the center wavelength is the spectral domain OCT center wavelength, 830 nanometers. And then this equation gives us the transversal resolution of around 19 microns. Okay, so it's actually very bad in comparison to standard microscopy system. And recently, we have a high resolution OCT, so-called as a OCT microscope. But even in this case, most of the cases, the resolution is something like 3 to 5 microns. It's still worse than a standard microscopy. Okay, please keep this point in your mind. OCT in general has a lower resolution than a standard microscope. But I'm not going to get into details in this lecture, but alternatively, OCT has a high imaging depth penetration. Okay, it's a kind of trade-off. And to overcome it, there are several techniques like an extended focus, it's optical trick, and also computational refocusing. But it's a slightly different story. It's out of scope of this lecture. Okay, so far I was talking about two resolutions. That was the first half of today's lecture. The one is axial resolution, and it is inversely proportional to the bandwidth. I mean, the wider the bandwidth, the better the depth resolution. And proportional to the second, or sorry, proportional to the center wavelength in its power of 2. Shorter the center wavelength gives you the better depth resolution. And the second point I told is a transversal resolution. And shorter the center wavelength gives you the better the transversal resolution. And wider the beam diameter, incident beam diameter, result in a better transversal resolution. And also the shorter the focal length of the objective gives you a better the transversal resolution. Well, in general, higher the effective numerical aperture gives you the better the transversal resolution. Okay. Let's go to the second half of today's lecture. Actually, this is the main topic of today, the sensitivity. It's a little bit elaborated theory. And I think this is one of the most difficult point for the beginning students of OCT. And today I'm going to give you a little bit, say, more details than we are normally talking. For example, in a kind of conference or something, we just briefly explain it. But in this lecture, I just a little bit digging into more for the sensitivity. And also, I'm going to clearly define several the conception and the terminology which are related to each other, but are a little bit difficult to distinguish for the beginners. Okay, so then let's start about the sensitivity. But before talking about the sensitivity, I would like to clarify the several terminologies, which includes the first, dynamic range. Okay, the second, signal to noise ratio, or frequently are called as a SNR, and then sensitivity. Okay, I think some of you guys have some experience of the OCT already, right? And you've used these three words, but sometimes interchangeable. Right? But this is actually, technically speaking, it's not correct. The dynamic range is dynamic range. SNR is SNR, and sensitivity is sensitivity. They have their own definition. They have something like a clear mutual relationship. And let me clarify this point first. Okay, on the first, dynamic range. Dynamic range is a parameter of an image, or let's say A scan. Okay, image or A scan. And the dynamic range is defined. Sorry, okay, I'm corrected now. Dynamic range is defined. Dynamic range is defined as the ratio of the highest and lowest values in the image. Okay, it's the property of the image. Sensitivity is not. It's not a property of the image, but a system, right? But a dynamic range is a property of the image. And for example, here it's one example of A scan. And here is the highest signal intensity, around 80 dB. And here is the lowest signal intensity, around maybe 35 in this example. So this means 45 dBs, the ratio between 80 dBs and 35 dB. Since it's dB log scale, the subtraction of it is a ratio, right? So 45 dB is the dynamic range of this signal. Okay, it's a definition of the dynamic range. It's a kind of easy, right? And then this dynamic range is in practice frequently limited by digitization resolution of a camera or a DAQ board. But there are several another limiting factor. But very frequently, it is defined by the camera resolution and the quantum resolution of the camera or DAQ. Okay. Then go to the next one. Is a signal to noise ratio, SNR. The dynamic range and the signal to noise ratio is not exactly the same. Okay. Dynamic range is a conception defined by the entire A scan or the entire image, right? You selected two different regions. One has a highest signal and the other has a lowest signal. And the ratio of it was the dynamic range. But a signal to noise ratio is about a conception about a single signal realization. Okay, but this single realization of the signal contains two components. One is a real signal, noise-free real signal, but some noise added on top. Okay, like here is a signal and the true signal, and the realization of the signal distribute around this point in complex domain. Okay, so then the signal to noise ratio SNR is defined by the ratio of the energy of the true signal and the noise signal. Okay, noise signal is defined by the variance of the distribution of the noise. That's the SNR. Okay, let me clarify again. Dynamic range is a concept about the image. So at least you need 2 points to define it. It's and two of them are realizations. But a signal to noise ratio can be defined at a single point of the image. And this single point, the signal realization or signal at this point consists of two components. One is true signal, and the other is a noise on top of the true signal. And the ratio of the energy of these two are the signal to noise ratio. So the dynamic range and the signal to noise ratio are exactly not the same. In this example of the A scan, hold on, I'm a little bit afraid about using this. Okay, it is working. Okay, the dynamic range is here. So from this, like the dynamic range is the ratio of the highest signal in the A scan and the lowest point of this entire A scan. Right? But a signal to noise ratio of, for example, this green guy is the ratio of this and this. Here it's something like a noise floor, but still it's a kind of approximation. In reality, we cannot define from a single A scan measurement that we need to measure the same point multiple times, okay, and then average it, and it gives you a quite good estimation of the signal, true signal. And at the same time, you can compute the standard deviation or the variance of multiple measurement. It gives you the estimation of the noise. And then you can finally define the signal to noise ratio. Okay, so it's two different points. To exactly determine the signal to noise ratio, you need multiple measurements. But to define the dynamic range, what you need is only a single measurement of the A scan or the image. Okay, and now the signal to noise ratio is particularly important to think about the sensitivity. Then the sensitivity, finally. The definition, let me start from the definition of the sensitivity. The sensitivity is defined as a maximum detectable attenuation of probe beam, okay, means 1 over minimum detectable reflectivity. Okay, let me think about it. Let's think about it. Maybe using this one. Okay, now the sample is assumed to reflect 100% of the light probe beam, I mean, and then assume you have this signal, right? And then reduce the probe beam or the reflectivity, sorry, the not probe beam, the reflectivity of the sample. So the first is 100%, right? And then make it into 50%, 3 dB reduction. So the signal drops for 3 dB. And more, the signal drops. And then finally, it varies in the noise. And then you cannot detect the signal. Okay, so this means the signal with the 100% reflectivity, the ratio of the signal at the 100% reflectivity to the noise level is the definition of the sensitivity. It's quite close or quite similar to the signal to noise ratio. Okay, but here we assume the 100% reflectivity of the sample at first. And this is not plausible. In reality, it is not. It is not realistic to have 100% reflectivity of the sample. Okay, so then there are several tricks to measure the sensitivity. But anyway, the point is, it's a ratio. This means the sensitivity is defined as a maximum detectable attenuation of the probe beam. Okay, so then how we can measure it in reality? Okay, here is the OCT system, and the probe beam is here, and I put the mirror. And the mirror is now assumed to reflect 100% of the light. But in reality, it's not, so we need to calibrate it in any way. We then put the neutral density filter of, for example, minus 30 dB in a single pass. And since it's double pass, it becomes double, attenuation becomes double, minus 60 dB. And actually, this minus 60 dB is a typical reflectivity of the biological sample. It's a minus 50 to minus 60 dB. or in linear scale, it's a 10 to the power of -5 to 10 to the power of -6. Okay? And then, so if, assume this guy, this yellow signal, if there is no attenuation, means if the sample reflectivity is 100%, 0 dB, the signal should be here. Okay? And then it reduced by the attenuation of the neutral density signal. And then here is the real signal realization. And the noise floor is here, right? So this means the ratio from this point and this noise floor point is the sensitivity of the system. But in reality, you are going to measure by the system is this signal to noise ratio. Okay, what we can measure is only the signal to noise ratio, not the sensitivity. But at the same time, we can calibrate or we can measure the attenuation of the neutral density filter. And mostly by using a standard power meter. And then you can put this attenuation on top of the sensitivity, on top of the signal to noise ratio. It gives you the sensitivity of the system. Okay, that's the point of the sensitivity measurement. Maybe some of you already experienced that the sensitivity measurement. And maybe, again, some of you blindly follow the protocol which was established by your precursors. Okay, but this, something I've explained here is the background exists in that existing measurement protocol of the sensitivity. Okay, so now the sensitivity, the definition is clear. And I'm going to dig into a little bit practical point. The sensitivity and the signal to noise ratio and also dynamic range is very frequently expressed in a decibel scale, dB scale. Okay, and just say gives you a brief introduction or reminder about the dB scale or dB. dB is the energy ratio. Okay, the energy ratio in a log scale, and if the ratio itself is a ratio of the energy, the definition of the dB is 10 log 10, a 10 log 10 ratio. Okay, a 10 log 10, 10, the second 10 is a basement of log. Okay, 10 log base 10 ratio. And is a definition of the dB if this ratio is the ratio of the energy. But if this ratio is the ratio of the amplitude, the definition of the dB becomes 20 log 10 ratio. Okay, it's quite easy. But the energy ratio is a squared amplitude ratio. Okay, and these two becomes here at the shoulder of this ratio, right? And then it becomes a ratio squared. It's an energy ratio. So essentially, these two equations are same. That if you define the ratio at the energy ratio, you should use 10 here. And if you define a ratio as an amplitude ratio, you should use 20. That is essentially these two equations are the same, and there is no ambiguity. Okay, and actually in old literatures, sometimes it claims there are two definitions of sensitivity in OCT. One is defined in 10 log 10, and the other is defined in 20 log 10 or something. But actually, his understanding is incorrect. It is always defined by the ratio of the energy. Okay, and if you use the amplitude ratio, you should compute it as a 20 log 10. And actually, it is exactly the same with the energy ratio. So there is no ambiguity. And let me a little bit exemplify this. So intensity or energy ratio is defined like this. It's a 10 log 10 of signal intensity divided by noise intensity. In the case of Fourier domain OCT, you can Fourier transform the original spectral interference signal, right, and have a complex signal, and can compute the absolute square of that complex signal. And if you compute the ratio of the absolute square of the signal, you should use 10 log 10. But you didn't square it, namely the amplitude of the complex OCT signal, you should use 20 log 10. Okay, and there is no ambiguity. And these two operations gives you exactly the same value. Okay. And then let me qualify the relationship and the definition of these three conceptions: dynamic range, SNR, and sensitivity. It's a recapitulation. Okay. First, what are they evaluating? The dynamic range evaluates the image property, but a signal-to-noise ratio is evaluating the signal realization, property of the signal realization. And then the sensitivity is evaluating the OCT system itself. So the OCT system property is defined in sensitivity, not SNR or dynamic range. Okay, but once you get the image from that system, the image property is defined by the dynamic range. And if you get a signal, one particular signal of the OCT, its property can be expressed by the signal-to-noise ratio. Okay, so these three conceptions are targeting on the different quantities. Okay, then let me summarize let me recapitulate the definition. The dynamic range is the highest to lowest signal energy ratio. Okay. On the other hand, signal to noise ratio is the ratio of the signal energy to noise energy. Okay. And the sensitivity is defined as a maximum allowable attenuation. And then the typical value, I also gives you a typical values. It can gives you some practical idea of how OCT is high sensitive. Okay. And the dynamic range of the OCT image is typically 20 to 50 dBs. But when you display it, it becomes something like a 24 dBs. In general, it's a 256 grayscale. And this 24 dB is something similar to the sensitivity of the eye, human eye. Okay. And the signal-to-noise ratio is also the same, 20 to 50 dB. But the sensitivity of the OCT is quite high. It's around minus 90 to minus 100 dBs. Okay. So this means 10 to the power of minus 10. It's a very high attenuation. Even the probe beam is very, very highly attenuated. Still, we can capture the signal. It's one of very big advantages of the OCT system. By the way, I also would like to remind another point here. The dynamic range and the signal-to-noise ratio is defined by the positive values, right? But the sensitivity is defined by the negative values. It is because the definition of the sensitivity is the attenuation. Okay? The reduction of the signal is expressed by the negative value of dB in dB scale, right? I mean the ratio less than 1.0. So the sensitivity is defined, technically speaking, sensitivity is defined by the negative values. But at the same time, very frequently and conventionally, this minus sign is omitted. For example, in a paper, you can very frequently see that the sensitivity of the system was measured to 105 dBs or something, plus 105 dB. But conventionally, this positive way of writing is accepted. But anyway, if it's written technically speaking, you can understand it's a minus 105. Then, so far, I was talking about the definitions of the sensitivity, dynamic range, and a signal-to-noise ratio. And then maybe you're interested in the real property, the practical property of the sensitivities of OCT, sensitivity and the signal-to-noise ratio of OCT, right? And now it's a mathematics, time of mathematics. Okay, what I would like to really discuss is the sensitivity. But as I've already explained, the sensitivity is proportional to the signal-to-noise ratio. Okay, when you measure the sensitivity, you need to measure the signal-to-noise ratio, and you can add something on top. It's attenuation, basic attenuation by the neutral density filter. So if we can understand the signal-to-noise ratio, It directly gives you the understanding of the sensitivity. So I would like to start from the signal-to-noise ratio. Okay. Then the definition of the signal-to-noise ratio in mathematics is actually quite simple. The ratio of the signal energy and the total noise energy. Okay. And then the noise energy can be split into three uncorrelated noise energies. The one is a short noise energy, and the second is a ring noise. The ring energy. Okay, rings N is noise, so it's not ring noise technically, it's ring. But frequently also we call it as a ring noise, but a ring. Okay, ring energy and the detector noise energy. And these three noises have different property. And I'm going to dig into in details in mathematics by using mathematics. But then anyway, let me start from the signal energy. Okay. The signal energy of the OCT is defined by this equation, this pseudo equation. The number of electrons generated by the optical of the light means electron number equivalent optical power of the detected probe. Detected probe divided by the pixel means the probe power is spread around the pixels in depth, right? And the number of pixels in depth, technically. Okay, so we need to divide it by pixels. And then this equation can be broken down into this equation. Okay, this guy, square root of IPIR, IP is a probe power, and IR, probe power on the detector. And IR is a reference power on the detector. And they are going to be multiplied, and then taking the square root. It comes from the basic OCT theory equation. I talked in the first installment of this lecture, right? The cosine term or the interference term of the OCT equation contains this guy. Okay, the OCT signal is proportional to the square root of IPIR. So it's here. It's a light power. Okay, and then there is some constant here. Eta is a detection efficiency or quantum efficiency of the detector. It means the conversion factor from the light intensity to the number of electrons. Okay, and then it's a Planck constant, and the center frequency is it's in proportional to the center wavelength. Means h nu 0 is the energy of the photon. Okay, intensity divided by the energy of the photon and times the conversion factor. And then exposure time. So this guy, except tau, gives you the number of electrons generated per time, per unit time. And then it is multiplied by the time exposure time. So this guy is the number of electrons generated in total, right? And it is divided by the pixel because this energy is a spread around the pixel, right? And then again, it is summed over the pixel. Okay, and the total energy is the summation of all of the pixels. And technically, and then this guy is squared because it becomes the energy. Okay, inside of the bracket is the amplitude, and it converted into the energy by squaring it. And then this energy is divided, is collected over the pixel. Okay, so this pseudo equation becomes exactly this equation. And then cleaning it up, and the n, for example, one n here survives, and the other is cancelled by this n. Okay, and this can be clarified like this. The square root is again cancelled by the squaring. And this equation. Okay, let's see on only the important point. This equation is proportional. This equation is proportional to the reference power and a probe power and a square of tau. Okay, the more the probe power gives you more signal energy in a power of 1. And the more the reference power gives you a more of the signal energy in a power of 1. And also the more the exposure time gives you more the signal energy in the power of 2. But then anyway, this signal energy only this sole signal energy is not it's not important. Okay, we need to always think about a ratio with the noise. Okay, but then anyway, it's a signal property, signal energy property. And then let's go to the noise part one by one. The first noise is a short noise. It is an inevitable noise caused by photon-electron conversion. So the point is, it's inevitable. We cannot eliminate it. The very theoretical and the principal noise. It's not the matter of the implementation. We cannot avoid it in physics. Okay, and then the short noise energy is defined by this equation. It's a number of electrons per pixel square root, and it becomes squared to make it as an energy, right? The amplitude of the short noise is square root, but immediately it becomes squared. So technically speaking, this square root is gone sooner or later. Okay, and then the point is the number of electrons per pixel. It is exactly the same with this guy. Okay, but anyway, we can see it. Now, but the equation itself is slightly different because here we are thinking about an interference term, the OCT signal term. But here, what we need to think about is a contribution of an interference term. Interference term itself has some energy, but you can forget about it. Okay, the probe beam and a reference beam independently contribute to the short noise by its power. So the equation can become like this: IP plus IR is a total light power on the detector, right? And then it is converted into the number of electrons. This conversion factor is the same with the signal energy and divided by the pixel number. Because what we are thinking is a per pixel, okay? And then squared. So the square root, this square root is gone by this square rooting. But there is another important factor here. OCT's typical light configuration. Reference power is normally much stronger than reflected probe power. For example, the reference power on a detector is typically configured as something like a 0.1 milliwatts to 1 milliwatt even, or 1 to 2 milliwatts, few milliwatts. In comparison, the probe power reflected by the sample and collected by the system and led to the detector is quite low, like 1 milliwatt times 10 to the power of -5. It's very smaller than IR. So we can use this assumption, and then in this term, we can omit IP. IP plus IR is quite close to IR itself. So we can omit this term. So then the equation becomes like this. It's quite simplified equation. Okay, rational but a simplified equation. Okay, then for the short noise, what we can see. Okay, this guy is again the conversion factor, and n is the number of pixels. And here, it's IR, means the short noise energy is in proportion to the reference power. It's a main message of the short noise analysis. Okay, keep it, and then go to ring. Ring has a slightly different property. The ring is defined as an intensity fluctuation of the light. Okay, intensity fluctuation. Amplitude of ring is a fluctuation of the intensity. So the energy of ring is a square of this. square of intensity. Okay, that's the point. The dimension of ring is square of intensity. Intensity is a square of amplitude. For ring, again, we need to square it. Okay, the ring energy, say a bit more details. It's again the optical power divided by pixels in electron square. Okay, but there is some kind of reduction factor of ring. It's an averaging effect. Since what we are talking about is fluctuation of the intensity, if we average it, fluctuation becomes small, right? More averaging result in a smaller or smaller ring. Okay, and we need to carefully think about that averaging effect, uncorrelated averaging effect, averaging of the uncorrelated signal. Okay, then this averaging effect can be broken down into three. The polarization averaging, and the line width is the wavelength averaging, and time averaging. Okay, let's start from the most difficult one, the polarization averaging. I'm going to skip the details of this, but a polarization averaging effect can be written as in this part of the equation, red part, 1 plus pi squared divided by 2. And here pi is the degree of polarization. If you know something about a polarization sensitive OCT, don't mixture it with the degree of polarization uniformity. The degree of polarization is a more fundamental physical property of the light. Okay, it's a randomness of the polarization of the light source. If the two beams has a different polarization states, orthogonal polarization states, they doesn't interfere to each other, and the photons are not correlated. But in this case, the energy can, the fluctuation of the intensity can be averaged out. So it's this effect, right? And if the light is fully polarized, the 1 plus 1, the pi is 1, so 1 plus 1 becomes divided by 2, 1. So there is no reduction of the ring. But light is depolarized, totally depolarized, pi becomes 0, right? So then this factor becomes 1 over 2. The ring reduced in its half. Okay. Here is the polarization averaging effect. And then the line width effect is here. Okay. And it's this one is say bandwidth of the light source in a FD-OCT, or say bandwidth of the light source in mu frequency divided by the number of pixels in a case of FD-OCT. Or the bandwidth of the light source, of the bandwidth of the spectrometer, say, and it is going to be divided by the number of pixels. So it's a resolution of the spectrometer. And in this spectrometer resolution, the light is integrated, so it's an averaging effect. So this term is the line width averaging. And here we have the inverse of the exposure time. Again, this one is averaging over time. More the exposure time, more the averaging. So it's inverse of the exposure time. The more T result in a more larger reduction. I mean, the smaller reduction factor close to 0. Right? If the T becomes infinity, this factor becomes 0 and no ring. Okay, and we also call it as a detection bandwidth. 1 over exposure time is frequently called as the detection bandwidth. More the bandwidth, we can catch more rings. And a smaller the bandwidth, we can reject most of the rings. Okay, now a longer T result in a smaller bandwidth and can reject more rings. Okay, and then the optical power. This part is the same with that of short noise, right? This one, but with a square root. The short noise is a counting noise. In some perspective, short noise is a counting noise of the electron. So it's in proportional to the square root of the number of electrons. But a ring is a square of it because it's a fluctuation of the intensity, not the amplitude. And then again, it's squared for the energy. And it becomes this equation, and I use the same assumption of reference power is much larger than the probe power. This equation is reduced into this equation. And it's still a bit complicated, but the point is this equation is proportional to square of reference power. Okay, the short noise is proportional to reference power in its order of 1, but now it becomes order of 2. Okay, and then the third noise, detector noise. The detector noise is quite complicated, but for this treatment, our mathematical treatment, it's quite easy. It's some constant defined by the noise in a detector. The point here is only a simple point. It is independent from the reference power and also even the probe power. Okay. Then summarize the point. So here is the signal energy, short noise, ring, and the detector noise. And it has different properties or a different relationship to the exposure time, probe power, and the reference power. Okay. And if exposure time increases, signal energy increases in the power of 2, the tau squared. And a short noise, but a short noise also increases, but in the power of 1. And a ring increases power of 1, and the detector noise increases power of 1. Okay, by increasing the exposure time, all of the noise increases, but a signal increases more. Okay, and then the probe power. By increasing the probe power, we can increase the signal energy in a power of 1. Here, this guy, right? IP. But the noise, short noise, ring, and the detector noise are insensitive to the probe power. Okay. And the most important point is the reference power. By increasing the reference power, signal energy increases, and short noise also increases in the same order. But ring increases double. I mean, in the power of 2. And on the other hand, detector noise is insensitive. Okay, so these 3 components of SNR has different properties for the exposure time, probe power, and the reference power. And then what we are interested in, the ratio of the signal and the noise, right? And to simplify the point, I would like to think about a situation, one of these 3 noise are dominant. We call it as a something noise limit. Okay? For example, short noise limit situation. If the system is working with a short noise limit, by increasing exposure power, you can increase the signal to noise ratio. Okay, similarly, if the system is ring limit, again, the exposure time increases the SNR, and also detector noise limit. So increasing the exposure time always increase the signal to noise ratio in the power of 1. It's 1 point. And then what's going to be happen if you increase the probe power? Okay, and it increase the SNR again for all of the cases. So using more probe power is most of the cases good. But reference power, sometimes some guys started the OCT from the interferometry background. Sometimes erroneously believes the reference power and the probe power should be balanced or something. This is not correct. Actually, it's a very slightly different property of the signal to noise ratio of OCT to the reference power. Okay, if the system is working with a short noise limit, the reference power is insensitive. The signal to noise ratio is insensitive to the reference power. No matter how you change the reference power, the sensitivity is the same. So surely the signal increases, but with the same speed, the noise floor increases. So the signal to noise ratio is the same. If the system is working in a ring limit, by increasing the reference power, SNR reduces. Okay, it's amazing. The reference and the signal increases, but more rapidly the noise increases. And if the system is in a detector noise limit, by increasing the reference power, the say signal to noise ratio increases. Okay, the signal increases and the noise is stands. Okay. Okay, and then I think maybe it's only yeah 2 points. Then now I think you can understand the sensitivity curve. Also in the textbook I show this curve, right? So here it's one of the typical OCT sensitivity curve. The horizontal axis is log on the reference power. Logarithmic scale reference power. Actually, it's log scale. The sensitivity is also displayed in dB. It's log scale, right? By increasing the reference power, the sensitivity becomes better and better, or signal to noise ratio becomes better and better. So here it's a detector noise limit situation regime, detector noise limit regime, and then it becomes stable. It's short noise limit, and then suddenly it drops. It's ring limit. Okay, so the alignment of the OCT, the point of the alignment of the OCT is making the system operating at the short noise limit, because short noise is an inevitable noise. So if the system is working only dominated by the short noise, it's the optimal situation. So you need to find out the reference power in which the system is operating at the short noise limit. Okay. But unfortunately, something you don't have the short noise window like this. Like if the ring of the light source is large, or noise of the detector is large, we don't have the short noise limit or short noise window. So in this case, you need to think about, in one hand, you can accept it if it's not crucial. But if you want to solve it, you need to think about a replacement of the light source or the detector. Okay. And then let me summarize the point. Okay. The first point of the second half of today's lecture is you can optimize the reference power to maximize the sensitivity, or the similarly SNR. As increasing the reference power and sensitivity, the first increases the detector, the sensitivity increases. Okay, sorry. As increasing the reference power, the sensitivity is first increases the detector noise limit. And then it becomes stable, a short noise limit, and you need to find out this regime. And then it decreases its ring limit. Okay? And the optimal sensitivity is obtained by when the system is operated in short noise limit. If the short noise window is closed, you may consider using a light source with lower ring, or using a detector or camera with lower detection noise. Okay. Then I'm going to give a short appendix of the sensitivity gain of FD-OCT versus FD-OCT, time domain OCT. And so far, I was talking about the sensitivity issues of Fourier domain OCT. But time domain OCT has a slightly different signal property and the noise property. Okay, signal energy of the Fourier domain OCT. Oh, okay, these guys of the Fourier domain OCT I've already discussed. But for time domain, the signal energy is slightly different. Okay, and this IPIR is divided by n/2. What is this? N here, in a previous discussion, N is the number of pixels in spectrometer, right? And then what is the number of pixels in image? After applying the first Fourier transform, it becomes half, right? The one is the positive frequency and the other is negative frequency, or the signal and the mirror signal. And the mirror signal is discarded. So this means the number of pixels in the image is n/2. And a time domain, when we think about the equivalent time domain system, it's a system with the number of pixel, depth pixel, n/2. So the light flow beam is spread into these pixels, n/2. Okay, it's a little bit difficult. Okay, let's explain in a slightly different point of view. light illuminates a sample from this direction. And then the time domain OCT scan each pixel by scanning the reference arm. So no matter where the reference arm, the sample of one line along the depth is illuminated. So this means for that line, the light energy is distributed. Okay? And we need to divide that light energy by the number of pixels. And now we have the energy of light per pixel. Okay, that is this term, n over 2. The probe beam is divided by this, and the reference beam also divided by this. And the shot noise, at this moment, I'm talking about only the noise limit station. Because the shot noise is a shot noise limit OCT is an ideal station, and most of the cases we configure the system to work in a shot noise limit, and it's the optimal station. Okay, the shot noise of the Fourier domain OCT is given in this equation. I've already talked about it, and again, this reference power is divided by n over 2. Okay, in Fourier domain OCT, IR is distributed into each pixel of the spectrometer. So it's divided by n. But now the IR is divided by all of the depth pixels. So it's divided by n over 2. And then compute the signal to noise ratio. And it becomes this equation, right? And this is already been shown in the previous discussion. And then the time domain OCT, this equation. This brown part is the same with the Fourier domain OCT, but we have this guy, n 2 over n, means the shot noise limit sensitivity of FD-OCT is n over 2 times higher than that of TD-OCT. It's a conclusion. Typically, n is, for example, 2048, the number of pixels in a spectrometer, right? So this means the sensitivity of FD-OCT is around 30 dB higher than TD-OCT if the exposure time, or say measurement time, is the same. It's very high, 10 to the power of 3,000 times high. 1,000 times? Yeah, 1,000 times high. Okay, and then maybe we can sacrifice this sensitivity gain a bit for the first measurement. Like if you operate the system 10 times faster, the sensitivity reduces as minus 10 dB. Okay, but this minus 10 dB can be compensated or more than compensated by this plus 30 dB. So finally, still we have 100 times gain plus 20 dB. Okay, so still the sensitivity of the FD-OCT is higher than time domain OCT. Okay, and now I need to talk about something I was lying in the first lecture. I explained as if like the high speed of the FD-OCT was coming from the absence of the mechanical scanning of the reference arm. But it is not really true. Even for the time domain OCT, we have several tricks like a rapid scanners or something. It can give us a very high axial scanning. But even though the time domain was slower than the FD-OCT. Why? And actually, that was because of the limitation of the sensitivity. We can make the time domain OCT fast and fast, but in this case, the sensitivity drops and the signal to noise ratio drops, and it becomes useless. So the real reason why we have high-speed Fourier domain OCT is this fundamental gain, the sensitivity. Okay, it's another point, hidden point. Okay, and the final slide. And then let's intuitively think about why two OCT systems have such kind of fundamental difference in sensitivity. Okay, it's a little bit magic, right? FD-OCT is faster than TD-OCT, but the sensitivity is high. Why? Actually, the throughput or the usage of the probe beam of FD-OCT is higher than TD-OCT. Why it happens? The light in a time domain OCT, each single point on a sample is detected by a single point of the measurement. It's like this, right? It's scanned along the depth. We have one depth signal, an A line, and we repeat it. And finally, we have a B scan. Okay? And in a Fourier domain, we illuminate the sample as a line along the depth, and I scan it by Gauss scanner, and we have B scan. Okay, but in reality, for both of the systems, the light illuminate as a line. Okay, in a time domain OCT, in this, it looks like the light scanning from the top to the bottom. But when you illuminate the sample, the light illuminates the sample along the depth as a line. So this means outside of this point, the light still exists, but it was not used for the imaging. It doesn't contribute to the imaging. So this means only a very small portion of the light can contribute to the signal formation of the OCT in time domain OCT, right? And actually, that's the number of pixel issue. Assume, okay, the number of pixels along the depth is n over 2. Here, n over 2 factor. So this means only one of n over 2 pixel contribute to the imaging. Okay, but in the case of FD-OCT, all of the light illuminate the sample can contribute to the OCT imaging. And this resulted in this factor, n over 2 gain. N over 2 gain of FD-OCT, or in a time domain OCT, the 2 over n reduction of the sensitivity in comparison to the Fourier domain OCT. Okay, that was something like the secret of the sensitivity of the Fourier domain OCT. Okay, so then here at the end of today's lecture, in the part time of the fundamentals of the OCT. And next time, I'm going to a little bit more talking about a little bit more talking about the optimization of the OCT, mainly for the selection of the wavelength and theory of the depth range definition. Okay. Okay. So then let's close the lecture. Thank you very much.